In this video we're looking at database concepts. This is 8.1 for the CIE 9618 course, Computer Science A-Level. Section 8, Databases, is a big section and there's several parts to it, so be prepared for quite a bit of information. So we could take a file-based approach to storing data on computers. But in a file-based system, each application might have its own separate data files, and the programs will be written to work directly with the structure of those files, so they're very closely related and dependent. A flat file means a table, where, for example, you might have transactions saved in a file, one after the other, just being stored over and over and over and over again, one after the other. And in this file there'd be duplicate information. For example, you might store the customer name every time they buy something, so you'd be storing the same name over and over again. So we'll have a look at some of the problems with a file-based approach, whether it's just files or a flat file. We'll look at the problems with those. So first of all, we get data redundancy. As we saw, we might store the customer name over and over again. So if you're storing any data multiple times, it's data redundancy. We also get data inconsistency because we've got the same data being stored in multiple places. If we update one or some of those places but not others, we have conflicting versions of the information. For example, you might have customer address in various places and then they move address, they move house. If you update some of the places you've stored it and don't update other ones, they're inconsistent and we don't really know which one's the correct address for the customer. The third problem we have is data isolation. So because the files might be separate and accessed directly by their own programs, there's no single program that pulls everything together. It's difficult to write that. The next problem is data integrity. Data integrity means making sure that the data is valid data or accurate data. Because we've got no centralized way to enforce the validation rules, then it can be broken and we get poor data integrity. The next problem is concurrent access. So if more than one person or program wants to access the same file at the same time, this can lead to lost updates or corrupted files. So we need something that would help manage that to avoid the problems of corrupted or lost data. And then number 6, security limitations. Access control is often all or nothing at the whole file level. Either you can access that file or you can't. It's hard to restrict a user to specific parts of the data. And number 7, lack of data independence. As we mentioned, the programs of files are closely related to each other. So if one changes, if the structure of the file changes, for example, then any program that accesses that file also has to change. So there's no separation between data and applications that use them. Number 8, it's difficult to scale this and maintain. If we keep adding new files and new programs, it becomes very complex. The relationships between the files and the programs becomes rather difficult to track, and there's no central schema to refer to, i.e. there's no central design that all these programs and files should be following. A better way to store large amounts of complex data would be in a database. And a database can be defined as a persistent, organized store of data. You'd have a database management system in your database, and that would help address the problems by using centralized storage, a data dictionary or schema, and features like transaction control and concurrent access management and security. So one of the approaches to a database is a relational database. In a relational database, the data is split up according to entities. Now, an entity is just anything we want to store data about. It could be an actual thing or a concept idea. Anything that you could store data about can be an entity. So for example, a customer is an entity. That's something we might want to store information about, and so is a transaction. All data about one entity is stored in a table. Within a table there are records, and a record stores data about one unique instance of the entity. Within the record you have multiple fields or attributes. Each attribute is one characteristic of the entity. For example, the customer's name, that's one attribute of customer. Attributes have data types, and they may also have validation rules. So this is the structure of a database from the top down. The database stores all of the data we want to store. So whatever our purpose for the database is, it stores everything we need. And then tables store data for one specific entity. So each table is dealing with only a single entity. And then within the table we have records, or what's called tuples, and that's the data for one particular instance of the entity. So one particular customer, for example. And an attribute is one characteristic or property of the entity. For example, customer name. So here we have an example with a table called book, and this is the book entity. It's being used to store the data for the book entity. We have a book ID, a title, and a genre. And we can see there that book ID, title, and genre are fields or attributes. They're the columns. And then a row is a record or tuple. So record B001, or so with the book ID of B001, that's a single record, and then B002 is another record. So an entity is just an object or concept the data is stored about. A table is the physical structure that stores the information for an entity, i.e. all the records for the entity, and it's organized into rows and columns. A record or tuple is one row of a table with all the attributes describing that entity. And a field or attribute is a single column of the table. Let's look at candidate keys and primary keys. So really we need things that identify the records in our tables. We want to be able to find them and find the right ones. So a candidate key is a field or combination of fields that could uniquely identify a record in a table. And a table could have more than one candidate key. For example, in this table we have book ID and the ISBN number, and they're both capable of uniquely identifying a record in the table. But the primary key is the candidate key that you have chosen to uniquely identify each record in the table. And every single record must have a value in that attribute, or combination of attributes, and it can't repeat. For example, we might choose book ID in this case to be the primary key, and ISBN is still a candidate key, but book ID is also the primary key. And we have secondary keys and foreign keys. So we can use secondary keys to help with searching, and we may not have the primary key available when we want to find something, so we can index the tables using secondary keys and make it much quicker to find things. So a secondary key is just a field other than the primary key used to sort or search for records, and it doesn't need to be unique. And then a foreign key is a field in one table that's the primary key of another table, and therefore it creates the relationship between the tables. It's effectively linking those tables together in some way. So in a relational database, one of the key things obviously is the fact that we have relationships between the entities, and hence between the tables. We could have one-to-one relationships. For example, a person only ever has one passport or one valid passport at a time. A book could be loaned many times. So the same book could be loaned out many times. And a student could belong to many clubs, but a club could have many students in it. So that's a many to many. So these are the three kind of relationships we need to consider. So in this example, we have a one-to-many book and loan, book being loaned many times. So if we look at the way it's created, we can see that on the left we have the book table, on the right we have a loan table. So this book is being loaned in the loan table. Obviously somebody's borrowing it, so we could say it's a borrow or a loan. But here we can see that the book's been loaned twice or borrowed twice. We see book ID occurs twice in this table. That means that there's a one-to-many relationship between these two tables. One book can be loaned many times. And a tip for working out which way these relationships go is we're looking for the foreign key, and the foreign key side is the many side. So in this case, if we look at the loan table on the right hand side, we can see the primary key for loan ID, for the loan table is loan ID. And book ID is marked there as a foreign key. So because a foreign key, remember, is an attribute in one table that's a primary key on another table. So we can see that the book ID is the primary key on the book table, and therefore where you use book ID in the loan table, it's being used as a foreign key. It's making that relationship between the two tables. It's linking back to the book table. So the side on which you find the foreign key is the many side. That's why the M is on the loan side and the 1 is on the book side. And in English again, it just means that the book can be loaned many times. As we see, it's been loaned twice there. And then a one-to-one example, you don't find these quite as often, but here's the staff ID and their card, their security card. So each member of staff has a card, but they only ever have one card. At least in this design, they only have one card that's active at any time. So this is a one-to-one relationship. You can see the staff ID on the right hand side there on the card table is a foreign key, but in this case it only ever goes back to one staff member on the left hand side. So it's only one-to-one. Now, many-to-many. Many-to-many relationships can't actually be implemented. So what we do is we split them so that there's no longer many-to-many, but just one-to-manys. So for example, in our situation where we had a student and club, a student could belong to many clubs and a club could have many students as members. We need to break that relationship up and create a new linking table in the middle. So we've created a table called Student Club, and it has a composite key that composes of the student ID and the club ID, and they're both foreign keys. The student ID is a foreign key to student, and the club ID is a foreign key to club. So we combine those two keys and make the primary key for the student club table. Now, as I said before, a way to work out where the relationship goes is to work out which side the foreign key is on. And we can see that the student ID is a foreign key to student, so that's the side that's the many side. And in English, it just means again that the student could have many student clubs, i.e. that student could occur many times in that student club table. So ST10, Priya, she actually occurs twice in that table. So one student, Priya, occurred many times in the student club table. And similarly, on the right hand side, we have club how do we know which side the many to one is on? If we look at club ID, we know that that's a foreign key. That's on that side, so we put the M on that side and the 1 on the other side. And in English, again, we have a club can have many entries on the student club table. For example, the chess club has many entries on the left-hand side. ST10 and ST11 are members of the chess club. So there's multiple members there. Okay, one of the things we need to do within the database management system is enforce referential integrity. That means that we need to make sure that the relationships are valid between the tables. So the rule is that every foreign key value must either match an existing primary key value in the related table, or it has to be null. And the DBMS enforces this automatically. It won't allow a foreign key in one table to point to a record in the other that doesn't exist. And that matters because if you had that, you'd be pointing. If you didn't do that, you could have records pointing to records that don't exist, and then you wouldn't be able to do queries. You wouldn't be able to get the data out that you want properly. So on the right hand side, there's an example. So imagine we were trying to delete a book from the book table where the book ID was B002. And that will be currently rejected in our database because we had loan entries that still reference that. So we can't leave them hanging and orphaned, okay, pointing at nothing. So the DBMS wouldn't allow it. We'd have to reassign or delete the loan records before we could delete the book record. Let's have a look at indexing. So as we mentioned before, we can index records based on the secondary keys. And this speeds up how we find the records. If we didn't have an index, i.e. we had no secondary key, we hadn't indexed anything, then the database management system is going to have to perform a linear search when we try to find a record based on a non-primary key value. And for a large table, that can be very slow. If we have an index, the index provides a separate sorted structure that maps key values to record locations. A bit like a book index. If you look in the back of a book and it has an index, it will help you to find the right page rather than having to go through the book from the beginning and look for every single page for what you're trying to find. So with this index, the database management system can jump straight to the matching record instead of having to scan every record. So primary keys are automatically indexed by the DBMS anyway, so you don't need to specify anything else for them. But if you want extra indexes, then you make secondary keys. Indexes do speed up the select and search, but they also slow down inserts and updates because you have to keep updating the index as well as doing the other operation you wanted to do. Alright, let's have a look at the scenario a bit more. So here we have 3 entities, book, loan and member. You see that the relationship there is 1 to many, so a book can be loaned many times and a member can loan many books or make many loans. The table book describes the physical books in the library. We have various books and book ID is the primary key. That uniquely identifies each row and there's no repeats. We have various attributes like title, author, genre, and whether it's available or not. A table member describes one registered library member. So attributes such as first name, last name, year group, and the date they joined. And the member ID is the primary key for this table. And then we have the loan table. So each record links one book to one member for a period of time. So that's how long they're borrowing the book for. So we can see that the primary key is the loan ID, but you also have foreign keys of book ID and member ID. And we can see here that book 2 occurs twice, which reminds us here that this is a one-to-many relationship. Okay, the one book can be loaned many times, hence it's appearing on this table twice. So if we link these tables together and look at the relationship a little bit more, we can see that the book B002 is on the loan table twice. So two separate loans, loan 1 and loan 3, but the same book. And different members, member 101 and member 104. And if we wanted to query this database and find out information, we might say something like the equivalent of show me every loan of 1984 and who borrowed it. So show me all the times that book was lent and who was borrowing it. So the DBMS can do this. What it's got to do is match the book ID to the loan book ID to find the loan rows. So it will match up B002 with B002 in both tables. And then it will match the loan member ID to the member ID. So M101 matches with M101, for example. And then that will allow it to find the borrower's name. And none of this requires duplications of the book titles or the member names. They can all be stored just once. So let's have a look at ER diagrams, or entity relationship diagrams, and why we use them. So an entity relationship diagram is a visual model that shows the entities in the system and the relationships between them. It also shows the cardinality of the relationships, i.e. whether they're one-to-one, one-to-many, or many-to-many. The reason we use them are to communicate our design to developers, clients, and teammates, so they can check it and see if it makes sense. We can catch problems early by making an entity relationship diagram before we actually start building the database. And it acts as a guide. So when we're creating the entities and making them tables, putting the attributes in, defining the relationships, we're using the entity relationship diagram as a guide. And the notation does vary. You'll see it done lots of different ways in different books and things. But in general, we have entities labeled. They're singular. This is one of the important things to remember. So it's pet rather than pets. Normally it's rectangular. It may give you the attributes as well as just the name of the entity. And then cardinality, again, various ways of showing the cardinality. You can label with things like 1 and M for one-to-many, or M and M, or 1 and 1. Sometimes people use crow's feet, different kind of line styles and shapes. So you'll see all kinds of ways of doing it, but the idea is always the same. The cardinality is either one-to-one, one-to-many, or many-to-many. And then you can also show tables with attributes and indicate whether they are primary keys and foreign keys or not. So in this example, they use color coding, but I prefer to actually write down PK and FK next to the primary keys and foreign keys, just to make it really clear. Okay, so how do we create an entity relationship diagram? Step 1 would be to identify all the entities in the problem. So you read the scenario and you pick out the nouns. The nouns. These are the things that the system wants to store data about. So you're just looking for the key nouns in the scenario. Then you're looking for relationships. So look at the verbs then. So the verbs that connect the nouns. For example, this borrows, they teach, they have, and so on. Those would be the things you're looking for next. Then you're looking at cardinality. So you look at the relationship and see, is that one-to-one, one-to-many, or many-to-many? And you have to reread the scenario carefully to work that out. The wording, obviously if you're an international student, English isn't your first language, that bit can be quite tricky because you have to look at the careful, detailed meaning of the sentences. And then you have to resolve many many-to-many relationships. So if you do find that there's a many-to-many, you have to split them up and make another linking table and then show that they're one-to-many relationships on either side. Here's a worked example. So we've got a vet clinic, and it says a veterinary clinic wants to build a database to manage patient visits. Each pet owner can register several pets, but each pet belongs to just one owner. Any vet at the practice can treat many different pets over time, and each pet may be treated by several different vets during its lifetime. The clinic also needs to record the date and reason for every visit. So remember, the first thing you've got to do is look for the nouns. So we're looking for things like pet and vet. They're two different nouns in there that are clearly important. But it also talks about a visit, and that's one that you might not immediately spot. So a visit is also a noun. It's a thing in this case that we want to store information about. Okay, and then we'd look at verbs like treat is the key verb here. Okay, register is a verb, so you can register pets and you can treat pets. So here we go. Then we have owner, pet and vet identified as the entities that we're interested in storing information about. And then we're looking at the relationships, so we know that an owner can have many pets, and we know that a pet can be treated by many vets, and a vet can treat many pets. So that's a problem. We've got the many-to-many relationship there, so we're going to have to do something about that, and we'll need to do that in the next step. So to split this many-to-many relationship up, we need to identify a new table to go between them, the linking table, and in this case we chose to call it visit. So a pet can have many visits to the vet. They visit on multiple different occasions, and each time they visit, a vet would be involved. On that particular visit, they would be treated by a vet, a single vet. So in this case, a vet can be involved in many visits, but only one vet is treating the pet on each one. Okay, let's look at our finished entity relationship diagram. We have the owner table there with a one-to-many relationship with pet. An owner can have many pets, that's fine. We've got a one-to-many relationship between pet and visit. One pet can make many visits. Sadly, the pet might get ill more than once. And then we've got visit to vet. Is vet to visit is actually one-to-many, so the vet can be involved in many visits. And that's ready to be built as a set of tables and implemented in our database. So some checklist points before you submit your diagram in an exam. So remember to always resolve many-to-many relationships. You can't leave them as a many-to-many. The foreign key, remember, always goes on the many side, never on the one side. So make sure the foreign key is in the right place. Check the cardinality and don't assume that it's the same as something else you've done before. Read it very carefully. It may be slightly different. Label every relationship line, so don't just draw a line, but make sure it's clear, labeled. Obviously there are different ways of drawing the lines, and you may be fine if you draw it with, say, crow's feet or another common notation, but it's safe just to say 1 and M or 1 to 1 or M and M. depending on what you've got and what stage you're at, obviously. And name entities as nouns in capitals, like owner, rather than something like owner's table, and make sure that they're consistent and use a singular rather than plural. So we'd say customer or pet, not customers or pets. Now we're going to have a look at normalization. When we're storing data in a flat file, the kind we looked at the beginning, we have various problems that causes. One of the problems it causes is called the insertion anomaly. So if we had tutors teaching students and we had a new tutor arrive, we'd have nowhere to store their information until they were actually assigned to teach a course. So that's a bit of a problem. Where do we create this data if we want to before actually assigning them to a course? Then there's the update anomaly. If the tutor name changes, we have to update it on every single row in that flat file. If we miss one, then we have the inconsistency problem. And then we've got a deletion anomaly as well. So if the very last student drops a course, i.e. there's no more students doing the course the tutor was teaching, then we've lost all the information about the fact that that tutor taught that course because we have nowhere else to store it. This is a flat file, so the only place that we're storing this information is in that file, and those records are now being deleted. So to get around this, one of the processes we use is normalization. We split this one unstructured flat file into several well-structured ones to get rid of the problems. Each stage of the normalization process fixes one kind of problem, and they all build on the one before. So we start off with unnormalized data. The raw data is it's just collected. There may be repeating groups, the same kind of attribute repeated in several columns, and it's just not normalized yet. So we start the process by checking if and trying to put it into first normal form. Now in first normal form, you can't have any repeating groups or repeating attributes. So every attribute would hold a single atomic value, one row per fact. So you can't have something like, if you had a list of hobbies, you couldn't have hobby 1, hobby 2, hobby 3, hobby 4 for a person. That's not allowed. You can't hold multiple facts like that on a single row. Then second normal form is it has to be in first normal form, and every non-key attribute, i.e. every attribute that isn't the primary key, then every one of those has to depend on the whole primary key and not just part of it. Now if we had a primary key that was a composite key, i.e. it consists of more than one attribute to make the key, then we might have a problem with second normal form. So if you can tell what the attribute is from just looking at part of the key instead of the whole key, that's a partial key dependency. So as you see there at the bottom, a dependency just means that you can work out the value of one attribute by looking at another. Now there should always be a dependency on the primary key, but for second normal form it has to be on the whole key and not just part of the key. Then in third normal form, we have to be in second normal form and have no attributes that depend on another non-key attribute. That's called a transitive dependency. So again, it just means that you could work out the value of one attribute just by looking at some other attribute that isn't the primary key. So here's an example of some unnormalized data. We have a couple of students doing courses, Amara and Tom. Amara does 2 courses, course C1 databases and C2 which is networks, and she's got grade A in course 1 and a grade B in course 2. Tom only does 1 course which is databases. So the problem we have here, first of all, this is not in first normal form because there's a repeating attribute or repeating group of attributes, we can see that the course ID and course name and grade occur twice, i.e. that's repetition. We also have a problem with wasted space because Tom doesn't actually do more than one course, so there's empty information for course 2. And that's just wasted space. Okay, that would be still using space, but it's wasted. And another problem we've got is that if we then decide that it's possible to do 3 courses, we'd have to redesign the table and possibly rewrite our software. So that's not flexible. It doesn't allow us to add more courses whenever we want. So the first thing we do is get this into first normal form. Remember, that means no repeating attributes or groups of attributes. Each attribute just holds a single atomic value. It can't be broken down further. So in this case, we now have student 1 occurring twice. Amara has to be recorded twice here, once for databases and once for networks. And then the tutor ID and the tutor name and grade can vary, of course, between those 2 courses. And Tom still just does the 1 course, so he only occurs in 1 row, whereas Amara occurs in 2 rows. So flattening this repeated group has solved the atomicity problem, and we can now have as many courses as we want. Amara could do more and more and more courses, and that's no problem. We just create more and more rows. However, we do have redundancy in that the same information is stored more than once. For example, Amara's name is stored twice, the tutor name Dr. Osei is stored twice, and this is duplicate redundant data. Now, in second normal form, we're looking for these partial key dependencies, and in this particular table, the primary key consists of student ID and course ID, i.e. there's 2 attributes and it's a composite key. So we have to look at the other attributes, each of the other attributes, and say, does it depend on that whole key, the pair, student ID and course ID, or just one part of it? So we look at student name, and student name actually only depends on student ID, because student names don't change when they do different courses. So that's a partial key dependency. Same for course name, tutor ID and tutor name. They all depend just on the course ID. They don't depend on the student ID. So another partial key dependency. The only thing that actually belongs to student ID and course ID together is grade, because that does vary for every single combination of the 2. Now, remember, if the primary key isn't composite, then there's no possibility of a partial key dependency. So if it was in first normal form, it would automatically be in second normal form as well. It's only when we have composite keys that we need to worry about this stage. So fixing the problem that we have in our tables, we're now going to split out attributes that only need part of the key. So for student, we created student course as well, and course Okay, so in step 2 we'll fix the second normal problem, and that means splitting off attributes that only need part of the key. So grade needed both, so that goes in a new table with student ID and course ID as the primary key, as the composite primary key, and that's the only thing left in the student course table. In the student table, we take out what we need, which is the student name, and that now relies on student ID. And the same for course ID, we take out those attributes, course name, tutor ID, and tutor name, that genuinely depend on the course ID, and put them in that table. So now it's in second normal form. There are no partial key dependencies. All of the attributes depend on the whole key. Grade depends on the whole key. Student name depends on the whole key. I mean, it's not composite, so it must anyway. Similarly for course ID. So all of those tables are now in second normal form. In third normal form, we're looking for the transitive dependencies. That means a non-key attribute depends on another non-key attribute. So you have to, again, look at the attributes and see whether that would apply. In this case, we have a course ID, and the course ID determines the tutor ID. So each course has a different tutor. But then we have the tutor ID determining the tutor name. So at the moment in our table, we have tutor name in a table that has course ID as the primary key. So Dr. Isay and Mr. Blake are the tutors, and it's saying that their name depends on the course, which is not really correct, is it? It's not a direct relationship. So what they really depend on is the tutor's ID, because the tutor ID is the unique identifier for a tutor. So this is in second normal form, but it's not in third normal form because we have a transitive dependency. I can tell what the tutor name is from an attribute other than the primary key. I can tell that it's Dr. Isay by looking at the tutor ID, which is not the primary key, and the same for Mr. Blake. I can tell because of the tutor ID. So we have to split the attribute that depends on another key attribute, non-key attribute rather, out of the table. So we're going to take the tutor name out, and we need to put that into another table called tutor. Now that has the primary key of tutor ID, as it should, because the tutor name depends directly on tutor ID. And that leaves the course table with just course name and tutor ID. Okay, which do depend directly on the course ID. The other tables weren't affected, and now everything is in third normal form. One way to remember third normal form is by the phrase, the key, the whole key, and nothing but the key. This is a variation of a legal oath that was said in the courts in England, which was, I promise to tell the truth, the whole truth, and nothing but the truth. So if you can remember that sort of phrase, you'll be able to remember the three parts, the three important parts to third normal form. That is, to put it in a more technical language, all attribute must depend on the primary key and have no partial key dependencies and no transitive key dependencies, i.e. they depend on the key, the whole of the key, and nothing but the key, nothing else, no other attributes. So you may be asked in an exam whether a particular table is in third normal form or not. So you can go through the stages to work out if it is. The first thing is to check if it's in first normal form, because it can't possibly be in third normal form if it's not in first normal form. So check all the attributes and see if they're atomic. Are there any repeating groups, repeating attributes? If there are repeating attributes or repeating groups, then you say no, this is not in third normal form because it's not even in first normal form, and you'd say this attribute repeats or something like that. So be specific and say what is it that's stopping it from being in first normal form. And then the second stage, if it is in first normal form, you want to look at the key, the primary key. Is it a single attribute primary key, or is it a composite key? If it's a composite key, then we have to do step 3, which is check for the partial key dependency. And then again, like we said, you just go through every attribute that's not part of the key and say, can I work out what it is by looking at just part of that composite primary key? And if you can, then it's not in second normal form. There's a partial key dependency. So obviously it can't be in third normal form either. And then finally, you're looking for those transitive dependencies. So again, you look through every single attribute in the table and say, can I work out the value of this attribute by looking at some other attribute other than the key attributes? And if you can, then it's not in third normal form. And again, you say why, you say something like this attribute, it has a dependency on that attribute, therefore it's not in third normal form. Okay, let's have a look at an example question. Here it says a gym stores bookings in one table called booking. It tells you the attribute names. It tells you the primary key is a combination of member ID and class ID, and it asks you to explain whether that table's in third normal form. An example table might look like that, with member ID, class name, instructor, and booking date. And the first thing we do is check to see if it's in first normal form. And all those attributes are atomic, they're not repeated, so it's in first normal form. And then we look for a partial key dependency. We know we've got a composite key, so it's relevant to look for partial key dependencies. What we're looking for here is member ID or class ID. So can I tell any of the other attributes just by looking at one of those? Can I tell the class name just by looking at the member ID? No. Can I tell the class name just by looking at the class ID? Yes. Okay, so spin is always class ID of CL1. Similarly for instructor, we can always tell that Joe Rays is the instructor for class ID CL1. So in this case, we're definitely finding that there are partial key dependencies, and therefore it's not in second normal form, and therefore it is not in third normal form. Remember, you have to answer the question, which was explain whether it's in third normal form. And we have to say no, it's not in third normal form because it's not even in second normal form, and it's not in second normal form because we have partial key dependencies such as class name and instructor depending on just class ID. So to do this kind of answers, mistakes that you make or students sometimes make, looking for third normal form first. Okay, so break it down, carefully look at each stage. First normal form, then second normal form, and then finally third normal form. Another mistake is checking for partial dependency on a single column key. So you can only get partial dependencies when there's a composite key. So don't even try looking for partial dependencies if it's not a composite key. And sometimes people mix up partial and transitive dependencies. So remember, partial means depends on part of the composite key, and transitive means depending on another non-key attribute that's instead of the key. Also, you should be naming the attributes, say exactly which fields cause the problem and why. Don't say things like there are some dependencies, that won't get the marks. And you can use dependency notation, so you can write things like class ID to instructor to make the argument explicit and easy to mark. Okay. So in summary, normalization removes redundancy and the insertion, update, deletion anomalies we saw. First normal form was no repeating groups, every attribute holds a single atomic value. Second normal form means it's in first normal form and every non-key attribute depends on the whole primary key, not just part of it. And third normal form means it's in second normal form and there are no non-key dependencies. To explain why a table is or isn't in third normal form, name the exact attributes and state the dependency explicitly. Okay, then that's the end of section 8.1. Next time we look at 8.2, which is the database management systems. Thank you very much.